we're a little bit behind schedule, but this is the observation and demonstration portion of the afternoon. So let's take just a brief break, meet out here. We're going to break up into groups of about 5 or 6, and then the interns are prepared to lead tours and to rotate around. These will be about a half an hour per station, about give or take, and then rotate, and we'll be done.
So we'll do one stress test on the board without the heatsink, and then one with the heatsink and the fan to show the difference, and we can see the difference on the thermal camera. So let's see. I think I'm gonna plug this in.
That's some hot food there. Cool knuckles. Monitor not been on?
No, it's on.
So how are you overclocking the Raspberry Pi if it has its own crystal in it for?
So there is the stress test that I run where I'm increasing the CPU clock frequency. I can change it in the code, and there's like a config file that I can modify to kind of have it overclock at different frequencies.
Okay.
Yeah. I guess this decides to not do it. That's fine. There you go. Alright. So there's these few commands that I run. There's this folder that I go to where all my temperature tests are saved. And let's do, so now I ran the test. There's like a 2 minutes or so idle time where it's gonna like start to slowly ramp up the temperature, and then a 2-ish minutes of stress test, and then 2 minutes of cool off period. So it takes a little while. It's gonna show up. This is like the baseline temperature we read, and then it's gonna start showing the frequency and everything on there. And I think we can see, is the camera pointed to the right, that one?
Yeah, it should be. This
Okay.
is the one without the heat
Yeah,
sink, right?
yeah.
What is a typical failure?
Failure on one of these?
Yeah.
As far as temperature goes, I'm not sure, honestly.
Yeah,
I mean,
it's
do you guys normally not get to the temperature to fail, or?
we don't really make it fail right now.
Okay.
We are not really overclocking it to the point of failure, but I would assume, like, because this is going, this temperature for the clock, the frequency for the clock is like base set at maybe 500, 600 hertz, and I'm clocking it to 1500 hertz. So I'm guessing if you would go more than that, that it could lead to overheating, because with 1500 hertz it goes to about 58 without a heatsink, or Celsius, 58 to 60 Celsius without a heatsink.
Let's try it, take it up to 2 gigahertz.
Well, that's how I just, so is this just a demonstration, or what are you looking for in this experiment?
So we just trying to show that without a heatsink, the temperature rises up to maybe like 60 Celsius.
You're just showing the
And with
effect
the
of the heat
heatsink and the
Okay.
fan, the temperature goes maybe up to 40.
Mhm.
And we were just gonna run it once, and then we can use that baseline as like to show you guys, because I have a nice little graph that Dr. Ali showed in one of his talks.
So we're going up. I mean,
Yeah.
this is real time here?
Yeah,
or
this is real time.
Snapshots?
Yeah.
snapshots of real time.
Yeah,
You can see the board starting to heat up too.
yeah.
Yeah.
And this usually takes like a little bit of time.
On your color scale on your
patience.
camera, what's hotter versus cooler?
So we have this, here's the scale over here, so,
Okay.
you know, red to white would be hotter, this purple to blue would be colder. Then we can move the mouse around, I'm not exactly
Okay,
sure.
so now it's idling at like almost a standard temperature at 600 megahertz, and then it's gonna go up in like a little bit and be like starting stress test.
So that's like its normal,
Yeah.
normal clock speed.
Yeah, yeah.
Do you know exactly where the temperature's being taken on the board?
I'm guessing there's like a temp sense under the chip. There's the temperature sensor.
Okay, now we're going up in frequency. Went up, went down. Up. We used to take those IBM ATs, you know, pop a 10 megahertz crystal into them, thought we were really doing something.
Yeah, these are now up to like
Gig.
more than, like tons of processing speed.
Yeah.
So while this goes on, did you wanna tell them about that
Oh, sure,
one?
yeah, I can do that while we're waiting to heat up. This device right here is our thermodilatometric analyzer. Essentially what it is, I can't slide this all the way out, we have this desk filled up, but this is a sample holder. It's used to measure thermal expansion of different materials. You have your sample holder here, you place your sample, which is this black bar in here, into the sample holder, close the chamber over it. As the chamber heats up, your material will actually expand and press into this bar right here, which is actually connected to an LVDT sensor, which essentially just correlates a displacement in the sensor to a voltage, and we can take that and then correlate that into a distance, a known distance. So we can get the coefficient of thermal expansion with this analyzer right here. And then in the other lab, we actually have a thermal conductivity analyzer as well. In the back is our DSC, which can give us, also you can get thermal conductivity off of that as well. And I think that covers all of our equipment up here for the most part.
So what are you using the liquid nitrogen for?
So that actually purges into the DSC right here, and it basically just provides coolant to the system.
Let's get some marshmallows.
So your samples, are you using a set group of materials, or do you make your own samples randomly from material?
So it's up, yeah. We've had different material combinations. For instance, I've had a couple universities reach out to me to test undisclosed, material types. Composite materials, even metals. I've done some metals or ceramics as well.
So now it's up to 1500 and you see the area around it starting
Yeah.
to heat up. It doesn't really show because this is itself, like the sensor and the chip itself is encapsulated, so that's why it shows blue on the top, but when you see around it,
Yeah.
it's stress testing and going up to 1500 megahertz. And at 1500 it's about like 49 to 50 Celsius. Yeah, it's slowly getting really hot.
So besides testing the Raspberry Pi, what do you use the Raspberry Pis for? And why'd you pick a Raspberry Pi?
What do I use it for? I use it personally at home for like emulating.
For everything, huh?
For everything,
Yeah.
yeah. But for us, we normally, like the last workshop we had, we also had a Raspberry Pi and we hooked up like a pressure sensor to it. You can even do like the test. I think half the people were doing the Air Vision Pro when we were showing the demo yesterday, but Dr. Kaya had this like flexible electronics kind of plugged in to an Arduino, you can do the same with the Raspberry Pi, and then it can, you know, have these applications where it can measure, like if you drop water, how, like, okay, there's water in this electrode, it's leaking, there's water in this electrode. So like it can be used for a bunch of different temperature sensors and.
So what's your best home
pressure sensors.
application?
Oh, I use it for gaming. Like I have a Nintendo emulator. But it's also easy to have like a Windows working station because I have a MacBook for personal
Yeah.
use. So if I need to run something on Windows, I can use that.
Wait, you're running Windows on the Pi?
Yeah, you could use like a virtual environment.
Okay.
Yeah, or like a gaming emulator similar to that. You have like for Windows too.
Yeah.
So now it's idling for like 2 seconds, and then we can see the output of how it looks like.
Mm-hmm.
You know, the heat transfer issue. So yeah, I think you should be seeing, you know, 30 to 40% knockdown on this if it actually, you know, works the way. And then on the IR infrared camera, you can see the colors. But did you as I showed them the grayscale as well?
No, I haven't yet.
Okay, so you will see the grayscale as well.
Step forward here if you want to go ahead and do that.
Yeah, I could
That
switch
way I can
it.
get it, that way I can just get a shot of it.
Sure, sure.
Hottest area and dark mean, you know, like nothing. So you will see.
Yeah, so the
It's very nice.
grayscale,
Yeah, okay.
There you go.
Yeah.
That's the grayscale.
So is that heat from the bearing of the fan, or is that heat from the,
It's the heat from the chip.
heat from the chip?
And it is actually just throwing the hot air out,
yep, so that's the grayscale.
you know, within the.
Tends to show a little bit more detail of the boards.
So you're exhausting all this heat into the atmosphere, and our
Yes.
meteorology students are then going to analyze how it affects the weather.
Yeah, because then, you know, for you.
So,
Ah, here is the guy.
yeah,
You're the master.
so I shouldn't drop it.
Thank you for don't drop it. Thank you. Leave it there. Leave it there. Thank you for don't drop it. Leave it like that.
Okay.
Okay. Who's next? New group.
This is your second group.
Ah, second group. Guys, this is the probe that we take to any water bottle. And then each one of these is, hey, should I tell you this? Because they start disappearing. Each one of these probe is 3,000 to 4,000. Yes, but get closer. I'm going to tell you. This is the Rolls Royce. This is a 10 years old Honda Civic. Yes, $20,000. $20,000?
Wow.
Yes, $20,000. Yes, $20,000. This guy, yes, has Bluetooth capabilities, and I purchased only the 10 meters cable, but this guy can go 100. Yes, so it's pretty tight, and the O-rings, as you can see, they're pretty tight. These probes are interchangeable. I put 5, and you are going to see which one are them. Can you read for them?
This part right here.
Yes.
pH.
pH,
What do you, optical? Optical DO?
dissolved oxygen. Yes, very nice.
No glasses, but I think it says conductivity upside down.
Oh, you don't need glasses. You don't need glasses. Conductivity. Come on, kid.
Turbidity.
Turbidity. This is a special one. This is the turbidity measure European style. In the United States, we are using the nephelometric turbidity unit. That is based in white light. This guy, that one, that is shining. This is the guy. This is based on infrared light. For that reason, it's called Formacine turbidity unit. Yes, and has a different calibration. What is the next one? pH, turbidity, and the center. What is the center?
Oh, there it is. Total algae PC.
Algae. So, the algae, the dissolved oxygen is calibrated with the oxygen in the air. So you move it, should read dissolved oxygen. Yes. And the concentration is 20%. Yes, so it's calibrated. But if you put it inside, so do we need to move from city or not? You can with the homework. You are the only one that is going to pass the course today. The other guys did not. So you read this ambient concentration is 35 and the value. So are we good or not?
We are very good.
That's why everybody don't live in Appalachia. Yes.
Yeah.
Yes. So we have these 5 sensors, and normally you go to the river, and this is to take a feeling about the quality of the water. Now we're going to put it in that water that our champion here went and get dirty his white shoes. Where did you get it? In a sewer? In a sewer, right? That is from the lake, yes.
It's from the lake? That's what the lake was?
From the river.
There's fish?
So, I would say that there is more than fish in the water. Yes. But the point is, guys, that the drinking water that you drink and do want to say salute, that is 0.5 nephelometric unit. 0.5. Now, can you tell me what is the turbidity of this? Who wants to put it inside? Come on. Please. Rule number one. Don't drop it.
Yeah.
Here, you hold this.
Rule number 1, never volunteer.
How deep does it?
You're going to read it. Put it there and move it around.
Turbidity must be pretty opaque.
He went to sleep the moment that you got it. What do you have? Press this button if you go to sleep. Yes.
Okay, the handheld.
So,
Want to hold your pop?
it's going to be FNU.
Okay.
Formacine, nephelometric unit. That's the one that gives you the turbidity. It's
FNU.
0.5? It's 0.5 like drinking water?
It's a little higher. It's
58.
It hits 62. 61, 62.
Good stuff. You could bottle that and sell it.
Yes, of course.
Health.
As what?
Mineral water.
Toxic.
Enhanced.
Or tonic.
All right, so what's
Cures
the
what ails
FNU?
you.
Formacine. If I am from Spain, it's formacine because it's with the C as in zebra. Formacine, nephelometric unit. Formacine.
Real high.
But you combine that with dissolved oxygen. What is the dissolved oxygen? Somebody can tell me. What is the dissolved oxygen?
Came back.
It's looking worse than when you started stirring. Yeah.
Yes.
Is that DO? No, wait. DO percent?
The DO should be maximum 100% because it's calibrated with the oxygen in the air.
173. 173.
Anybody can explain why is 173? It should be maximum 100? Common sense.
The last class dropped it.
What's bad
Question is
calibration?
why if the instrument is calibrated with the oxygen in the air at maximum should be 100%.
It's maximum for air.
But this is in percentage, no? Percentage of the saturation at ambient conditions from the air. Now this is reading 183. Why is that?
183%.
Yes, 183% of dissolved oxygen.
Because of all the garbage in the water.
You are in the right direction.
Yeah.
Can you explain
Give
a
an
little
awful-
more?
Yeah.
The physics lady, the mechanical engineering lady.
Geology. I haven't taken my groundwater class yet, so I might get this wrong. But you,
Decaying,
plants in the water. or
Pardon?
like
Yes.
Plants and fish. Plants
Yeah,
in the
there's
water.
plant-
Yeah, plant life.
Plants, close and close.
Yeah.
What kind of plants?
What is the physics that the sensor uses? How is it determined if it's all bouncing?
It's why he has to be here.
So it's trying to do photosynthesis underwater.
But basically, he's taking vengeance. Yes. You're asking me funny question. Now I'm going to ask another funny question.
get
Yeah.
close up on that or not.
I can't tell for sure if I've got it or not.
It's all
No,
glare.
I'm going to explain it, guys. You see the DO is too high and the turbidity is very high. Yes? No, there is another sensor that is algae there, but I don't know if my partner already calibrated or not. The reason for that is you calibrate that with the air, but the water can have more than the saturation. Remember that the water that is in the surface is getting at equilibrium with the oxygen in the air, right? Yes. But if there is anything in the water that is producing oxygen, the oxygen content of the water is going to go up, and that is called algae.
Yeah.
So, to say it in a very nice way, because there are two ladies here, there is a lot of nutrients in the water.
And where do those nutrients come from?
A lot of they are coming from the S word. Yes.
Snails.
Yes. or I can see that probably they are putting some nutrients in the grass, and the water is trickling to that body of water, and the nutrients make the algae, and the algae start producing oxygen.
So we can bottle this and sell it as a high oxygen health drink.
And with the benefits that they are going to build your immune system.
Yeah, right.
Right.
If you survive.
Yeah. Don't
you
vaccinate, drink this.
Yes.
So what would a healthy like waterway oxygen level be?
96.
Gotcha.
And in winter, the oxygen levels go very high because the solubility of the oxygen is inversely directed to the temperature.
Sure, yeah.
Yes. If you boil the water, the oxygen escape.
Yeah.
If you freeze the water, that's why the Coca-Cola, when you put it outside, it start making bubbles on the outside because the CO2 start getting out. So basically, nasty water.
Yeah.
Don't drink it. Don't swim in that because eventually you're going to absorb things. So, and that is my particle counter. Your homework. You need to go there, pick up the piece of paper, flip it, collect what is the PM10, the PM25, and you are going to tell me if we need to leave this town or not. Yes, because the format contains the National Ambient Air Quality Standard for the United States. That is air pollution, this is water pollution, and inside I have my spectrometer. Do you want to see what is the alkalinity of this? Probably, yes.
I want to see your mass spectrometer.
The 6,000, yes, the mass spectrometer, yes, this is the one. So nobody wants to come to my beautiful mobile lab because it's too hot.
Can I have a look inside?
Yes.
Another 4. They're all over the place.
So guys, this is $6,000. This is the working horse. This brand, the Hatch.
Yeah.
You find it in all the drinking water plants and the wastewater treatment plants. The Hatch. Why? Because with this little thingy and a lot of those microchips that they made, yes, you can have 2,000 analysis here. 2,000 analysis that they're already saved. So what we are going to do, I need somebody that do not have shaky hands. Don't drop my baby. Yes. Thank you. Rule number 1.
Okay.
Don't drop it. Remember. Now, do you want to do? Now, this is how you make money. You came for environmental, yes, wisdom, but this presentation is about how to make money. Yes. Number 1, you hook the guys first with that little device that do everything for you. Then you get them addicted to this little thing.
You saw them do that.
Yes. Do you want to do the analysis? You need to purchase this one. Yes.
And what's the cost per unit?
Don't ask me.
First one's free.
Every time. The first one.
That's how you get some hooked, yeah.
Yes, the first one. Yes. So you put the little water. Rule number 1.
Don't drop it.
Don't drop it.
Nobody remember that.
Nobody get nervous. We're gonna break it.
Now, then you are supposed to take your water sample from there with this one that is disposable. You can put it in your pocket. Take it there and take exactly the quantity that requires. And you are touching. She's touching with the fingers the glass. Dr. Ramirez, Never touch the glass because the glass is going to be raised by the spectrometer. Yes, my fault. So this is going to be for demonstration next time. Yes. Now, the nice part is, get together, come here to the center, is, let me see, this is the one? Ah, yes, this is the one. Then you put the sample water, yes, put it here, until the mark, whatever is the mark, yes, then you check it until change the color.
Shake this.
Put it there. No, not that one. And because this is a spectrometer that is shining a beam of electromagnetic radiation, yes, we don't want this weird light. Then you put this one on top, and then you turn it on, select the right method, yes, and then hit the button to start, and then you get your alkalinity measurement. The terrible part of this is you lose the feeling that putting the acid, putting the other one, yes, and you have the feeling that I am neutralizing something. Here is the white or the black box that all the kids are accustomed today. They say, this little black make me happy all day long. Yes, but I have no idea what is this. Yes, that's how that works, the spectrometer. And this is what normally the EPA uses for analysis in the field, because they need to take decisions today. You need to abandon this immediately.
Right.
They have a little more sophisticated things, yes? And we have our own diesel generator, yes? But this was a laboratory van that belonged to one petroleum consulting company. And because we are in the petroleum field, I wrote one grant to the Ohio EPA, and I proposed to take the instruments to the schools, so they don't have to spend $50,000, yes, in these three things, yes, $50,000, and they can have the experience, yes, and connecting the dots. That's the idea. Now we need to put this one to work, but everybody needs to touch that one, and to see the screen. Please, somebody. And you don't want to drop it. I know you don't want to drop it.
I don't.
Yes, I know. I'm going to put it here.
Yeah.
You are going to investigate who is the
$30,000.
This is the hard.
All right.
How do I turn it on?
Number one.
I already tell her that it's great here.
I wanted to jump on his case about having that diesel generator. What's that doing to your?
Oh, yeah, yeah, why don't you have a diesel
I
fire?
didn't like the.
Okay. Looks like the air quality is pretty good in this spot.
Yep.
Well, you can see it.
Awesome, great.
So I have a little CO2 monitor on my desk. When I get huffing and puffing, I can watch it. Watch it go up.
Well, I'm going to program the robot. See this block right here? So I'm going to put it in here. I should be able to put it in any orientation, and the robot should be able to see it and pick it up. Okay? So the first thing you have to do is you have to calibrate the camera to the calibration grid. Okay? And so if this calibration grid, if you look on your paper here, this is the calibration grid. And the dots are 15 millimeter center to center. Okay? And so this is how this grid is mapped onto the back of this camera. This is a CCD camera, and you can see that the resolution is 1024 by 768. So somehow I got to get these dots here mapped on the back of this camera. And so I calibrate it, and you can see here, so this center dot right here, that's dot number 1. You can see dot number 1 here, that's 0, 0. Okay, and then the dot number 2, I go in the X direction, plus 15, which is this thing. And then you can see, so these are the points on the calibration grid, and this is how it's mapped onto the back of the camera. That's the first step. Okay, now this is a 2D vision process, So I calibrate it to this tabletop is basically my user frame, okay? So then my next step is I put this here, so the camera's calibrated. So then what I do is I take this, I pick up an object that I want to pick up, okay? And so what I do is now I have to create a vision process to this part, okay? So that I can put this part here, and I usually just put the part in. That is the reference position, okay? And I go through and I go down and I pick and place and all this, and and record all these points into my program here, okay? And then what I do is if you look on the screen over here, is if I take the block and I stick it here, and you can see the green line around the block. You see that? So then that means this camera can find it and pick it up. If there's no green around it, it can't find it. Okay, so then what I can then I have to train it with the part. There's a certain threshold, and so the reference part I can find 100% of the time. But then I start putting in my other parts in there, which there's variability of those other parts, and so there's this threshold number that I keep lowering until I can see all of my parts given my certain environment with the lights and everything like that. Okay, and so after that, okay, then I take that vision process, and you can flip the page. Here's creating the vision process. Then here's the program that I stick it in. Okay, so there's you can see here there's two vision routines. You know, it's the run find. It's find the part. Then the next thing, when it finds the part, it finds the offset of how this thing is oriented, and I just stick that into another routine with the orientation, and it finds the part. Okay, so here we just try it. So
now, does that have the green?
Yes. Yeah. So I should put that in any orientation.
Okay.
And if there's no green there, I can't find it. So my program would just loop until it finds something. Okay. So here I just run this. Here, it'll find it. Now this robot's slowed way down because it's a training robot. If this was on a job floor, they're really super quick. You know, so here it goes up to the home position, and it's just looking for a part. And if you can see the program, it's just looping. But then when I put something in there, it finds it, hopefully, goes down, picks the part up. So it's a two-step process. You calibrate the camera to the calibration grid, and then based on your part, you create a vision process that you can stick in your...
So if you slip one in there real quick, will it go after it right away?
Yep. Yeah, so here. When that's done, I'm gonna... This thing is logged out. So if I put that in like that, it's gonna find it right away.
Now what button are you pushing here?
This is the forward button. This is see, this thing right here, it's a safety thing.
Okay.
Because like it
Yeah.
stops. Because you have to make sure. As long as my hand's on this thing, you know. And you can put two in there as well. As long as it finds one of them, it'll find it. It'll find that. Pick it up. So this is probably the simplest vision process, but it has all the components. You know, there's 3D vision as well, which, you know, I've seen them where they've had parts just thrown in a bin, and it goes on and just picks them all up. Here, you want to try it? Okay, now hit the forward button.
Just keep hitting it?
No,
That's good.
here you go.
Yeah.
I think, I don't think you have to do anything.
I don't need to do anything to
No.
start it.
Just okay. Let it go. You may have to hit forward.
Yeah, it's going.
Oh. The reason why I keep hitting forward because I usually have it in step mode,
Yeah.
and so I got it. I step through every line by line by line. But yeah, so you can try it if you want.
Okay, I'm gonna let off on the, so here's the little switch you have to.
So just hold that down the whole time?
Yeah.
Yeah.
If not, if you let go, it quits. It's a safety feature. It's called a dead man switch.
Hold shift and press next.
Oh.
This is not with demo. So basically, as you see on the screen, that's two robots. I'll try to keep my head still so it doesn't jitter so much. So in this case, we have two robots here. So one of them is the physical one on the left, and then you see the virtual one on the right. There's some assumption here. The camera feed from the HoloLens is going to be a little bit delayed. So in this case, we implemented this using HoloLens from Microsoft. It's HoloLens 2. It's an AR device, augmented reality device. The difference between this one and the Meta Quest 2 or 3 that you've seen, that's a VR device where the entire field of view is virtual. In this case, it's going to be a blend of physical and then virtual scene. Okay, I'll try to keep my head still. So in this case, we have two robots here. And basically, we implement so that the virtual one mimicking the movement of the physical one, but we can still send the command from HoloLens itself to the robot to move into a certain position. So in this case, let me try and move it to the home position. Yes, you will see the physical one move a little faster than the feed, but that's because the packet delay is have to go over Wi-Fi, come back to that computer, so the feed is a little delay. So and then we can move it back to another position down there. So in this case, we try to aim, the project is for training the workers so that they have a virtual environment that they can play with. They don't have to actually train using the physical one. It's like part of the training. We also experimenting with a capability that worker can program the robot using the virtual environment alone without having to use the TIS pendant. We're still working on that, so let me try. Hopefully that works. Disconnecting. Okay, that doesn't work. Yeah, so that's why we don't have the like from the virtual one move the command back to the physical one. Yes, that's still a little buggy, but we are working on that still. Any questions so far?
So you're designing this platform? This isn't something that's on the market. You're designing a new.
So far we haven't seen, but I think other people try to rest and develop it maybe. But we basically have the application query the joint angle data from the physical robot and then mimicking it on the virtual one. So we are defining the platform, but some of the API is available for the, from the robot itself. So that facilitates the integration.
Okay, but you're not working with Universal to develop this?
So far, no.
Okay. Mm-hmm. Do they know you're working doing this?
That I'm not sure. I'm just basically a developer. I'm not the high-level management on that side. That's above my pay grade. So in this case, this one is the digital twin demo. Anyone want to try it so far? No? Okay, come on. One quick note.
Do I need to take off my glasses?
That would be ideal. You can try to fit it in.
Oh, sorry.